Hi KCET 2026 aspirants, welcome back to Sankalp series. So as you all know, we have started the second chapter of chemistry, that is electrochemistry, and today we are in part 3 of this chapter where we will be talking about the conductance of ionic solutions or conductance of electrolytes. Okay, so you can see here conductance of electrolytes, and if you want the PDF or notes of these classes, do join our WhatsApp channel. The link will be there in the description section of this video. You can download it from there. Okay, fine. So as you all know, we have already completed part 1 where I have talked about introduction, electrochemical cells and galvanic cell. Then in part 2 we talked about electrochemical series and Nernst equation. Then today we will be discussing part 3, that is conductance of electrolytic solutions. Okay, so let's see what we have in today's class. What are the topics that we have in our today's lecture? So first we have important terms and definitions. Second, I have conductors, insulators and semiconductors. Third, electrical conductance. Fourth, I have ionic conductance, measurement of conductivity of ionic solutions, molar conductivity, variation of conductivity and molar conductivity, and lastly I have Kohlrausch's law. So in today's class we will be learning a lot more new formulas, definitions and concepts. So please sit with your notebook and a pen and write down all the important things, and after that we will be solving important questions as well. Okay, so first, if I talk about what is resistance, so important terms and definitions that you must know before understanding ionic conductance. So the first one is resistance. So if you have studied physics, you know resistance is the restriction to the flow of current, right? And it is denoted by letter R. Okay, it is denoted by letter R. The measurement unit, it is measured in the units of ohm, and these are the things that you should keep in mind. So let me highlight these things. So it is represented by symbol R. It is measured in the units of ohm. Then you have the symbol of ohm is this omega, which we use, and it is directly proportional to length and inversely proportional to area, right? So R is proportional to rho L by A. This is the formula that you should be knowing. Now to remove this proportionality, what we do, we multiply a constant, and that constant, this rho constant, is nothing but resistivity. Okay, so resistivity, it is a constant of proportionality. It is a constant term. It is called as resistivity. It's SI unit. So you can see here, if I just write down what will be the form of rho will be equal to R A by L. R unit is O, right? Area will be in meter square or centimeter square. Length will be in meter. So if I cancel, I'll get ohm meter, right? So what will be the unit of rho? Unit of rho will be either ohm meter or ohm centimeter. Clear? Next, it is also called as specific resistance. Okay, this is very important because in question sometimes it might be written specific resistance and you may get confused. So you should know it is also called as specific resistance, but the most common term used is resistivity. Okay, next, what is this definition of resistivity? So resistivity will be equal to resistance when the area of cross section is 1 meter square and length is 1 meter, right? So that is what is told. The resistivity for a substance is its resistance when it is 1 meter long and its area of cross section is 1 meter square. Okay, so for any substance which is 1 meter long and has a cross sectional area of 1 meter square, the resistance that it offers, it is only its resistivity. Okay, like for example, I'll just give a very simple example. Suppose you have a suppose you have a rod like this. Okay, and suppose this rod is like this. Okay, and we have this rod length is 5 centimeter. Okay, and this cross sectional area is suppose 7 centimeter square. Okay, so the resistance that is offered, so let me divide it like this: 1 2 3 4 5. This is 1 centimeter. Okay, and this area suppose is 1 meter square, this much. Okay, so this much, the resistance that is offered by this particular area, which is having a length of 1 centimeter and an area of 1 centimeter square or 1 meter square, that is the resistivity of that substance. Okay, the resistivity is equal to resistance when the length is 1 centimeter square and the area is, length is 1 centimeter and area is 1 centimeter square. So whatever resistance is offered by this area, that will be equal to your resistivity. Okay, I hope this is clear. Fine. Now let us understand the next term. So first two terms are over. Next I have two more terms, that is conductance. So what is conductance here? Conductance is very simple. You should know it is inverse of resistance. Okay, inverse of resistance, and it is denoted by symbol G. Okay, this is important. It is denoted by symbol G, and its unit is Siemens, and we rewrite it in the form of S, and it is equal to ohm inverse. Inverse of resistance 1 by R or 1 by ohm, so that is ohm inverse or omega inverse. So you can write G is equal to 1 by R, and the formula of R is rho L by A. So this is there. Now what is this 1 by rho? Okay, here this 1 by rho is replaced with kappa, and that is the next term, that is conductivity. Okay, so what exactly I have done here, see, this can be written as like this, 1 by rho into A by L, and now this 1 by rho is replaced with another letter, that is kappa or K and A by L. This K is called as kappa, which we will study here. Okay, so conductivity, this is called as conductivity, kappa is called as conductivity, and it is inverse of resistivity. Okay, and it is represented by K. Then what is its unit? You can see the unit is, see, you can see the unit here. You have what will be the value of kappa here? Let me just derive the units here. So I can have kappa is equal to, or you can write, see, R is equal to rho into L by A, right? Then 1 by rho, I have taken here, that is equal to 1 by R into L by A, right? Now 1 by rho is kappa, 1 by rho is ohm inverse, and this one is meter inverse, right? Or I can write S meter inverse. Okay, so that is how the unit has come. In meter or centimeter you can write down. So SI unit is either S meter inverse or S centimeter inverse. Okay, so please remember this one. Next, it is also called as specific conductance. So this is also called as specific, sorry, one second. Yeah, so this is also called as specific conductance. Okay, like you have resistivity also called as specific resistance, we have conductivity called as specific conductance. Again, you should know this so that if this term is used in the question, you don't get confused. Next, we have conductivity of a material in S meter inverse is its conductance when it is 1 meter long and its area of cross section is 1 meter square. So you can see this is the formula of conductivity, kappa is equal to 1 by R into 1 by LA. So this can I write like this, this one can I write like this, kappa equal to, what is 1 by R? 1 by R is resistance, which is G, G into L by A, right? So I can say that conductivity is the conductance when this length is 1 meter and area is 1 meter square, right? We have the definition for resistivity, same is the definition of conductivity. Okay, let's again understand this with a simple example. If this rod is there, okay, and I'll take the same number, suppose this is total is 5 centimeter, this is 1 centimeter. Okay, this total area is suppose 5 centimeter square. Okay, this total area is 5 centimeter square and this much is suppose 1 centimeter square. Okay, so this much area, okay, this much length, this conducts how much, what is the conductance of this particular area, how much electricity this particular area can conduct, that will be equal to your conductivity, or we can call it as kappa. Right, so kappa is the conductance when the area is 1 centimeter square and the length is 1 centimeter, right? Okay, so we have understood these terms. Now let us move to the next term that you should be knowing. So I have just summarized this first 4 terms so that you don't get confused. Resistance is R, resistivity is rho, and conductance is G, and conductivity is kappa. And you should remember here, resistivity is also called as specific resistance, and conductivity is also called as comment and tell me. Okay, fine. Now we will go to the next topic, very small topic, and I think all of you should be knowing this topic: insulators, conductors and semiconductors. So those materials which can conduct electricity through them very easily are called as conductors. We have example, metals. Okay, generally metals and alloys are good conductors, but there are also certain non-metals which are good conductors like carbon black and graphite, and organic polymers. Similarly, what is insulator? Insulator is something which has low conductivity or which cannot conduct electricity easily. Example, here we have glass and ceramics. Next we have semiconductors. So these are those substances which have conductivity between metals and non-metals. Okay, sorry, between insulators and conductors, means they are not very high conductors as conductors or not very poor conductors as insulators. They lie in between somewhere, and the example here is silicon, gallium arsenide, doped silicon. These are the examples of semiconductors. Now apart from this, conductors, insulators and semiconductors, any other thing, any other material or any other compound can you think of? Just take one time, and if you know, just comment down. I'll show you the next type of compound we have is superconductors. Okay, so what is superconductors here? So there are certain metals called superconductors by definition which have, this is very important, which have zero resistivity. Okay, which have zero, so it might not be visible, wait, yeah, which have zero resistivity. Okay, these have zero resistivity or infinite conductivity, means they can conduct as much electricity as is required. There is no resistivity at all. So what are the examples here? So earlier there were only certain metals and their alloys at very low temperature, like up to 0 to 15 Kelvin we can say. There were certain materials which were supposed to have the superconductors nature, but it did not stay forever. There are many other new compounds, like today's we have ceramic materials and we have mixed oxides which also show the superconductivity at temperature of 150 Kelvin. Okay, so at certain high temperature also we can have superconductors, and they are ceramic materials and mixed oxides. Okay, so these are the important things. I'll clear the slides so you can see properly. Now we will move to next thing, that is electrical conductance. So electrical conductance is what? Electrical conductance is due to the movement of electrons. Okay, you can see why metals are conductors. You might have studied in class 10th as well. Metals are conductors due to the movement of electrons in them. There is presence of free electrons in the metal because of which they can conduct electricity. Okay, so what are the factors affecting electrical conductance? So we have 3 important factors. One is the nature and the structure of the metals. Okay, next you have number of valence electrons per metal. If more number of valence electrons are there, better will be the conductivity, right? Next we have temperature. So when you increase the temperature, the electrical conductance decreases, right? When you increase the temperature, there is more collision, there is more resistance, so conductance decreases. Next we will talk about ionic conductance. Now why ionic conductance is there? This is due to the movement of ions. Very important. Okay, you might have what I'll say, you might have heard this suggestion or a precaution that never touch your switchboards or electrical appliances with wet hands, or what is the reason for that? So now you see, generally if the water is not pure, it has a lot of ions in that. Okay, and these waters are very good conductors of electricity. Okay, not very good, but they are good conductors of electricity. So now if you are having water in your hand and you are touching some switches or electricity, the electricity will flow through your body. okay, and as a result of which you can get a shock. So that is why it is highly recommended, suggested not to touch electrical appliances with wet hands, right? So there is no ions, there is no electrons inside water. There is ions which conducts electricity. If you can take a salt of NaCl solution and connect it, you will find that the current will pass through it. So what is the things that is conducting electricity in an NaCl solution? It is Na plus ions and Cl minus ions. So in ionic conductance is due to the movement of ions. So what are the two factors through which electricity can be conducted? It is due to the movement of electrons or movement of ions. So movement of electrons generally happens in metals and movement of ions happens in electrolytes, okay. So what is the factor that is affected here? So first of all, the nature of the electrolyte. So now this nature will talk in detail. So we can have either a strong electrolyte or a weak electrolyte. You might have studied in class 11th in the ionic equilibrium chapter regarding strong bases, weak bases, strong salts, weak salts, strong acids, weak acids, right? So if an electrolyte means it has one positive ion and a negative ion, okay? If it can dissociate easily, if it can form more number of ions, okay, then it is called a strong electrolyte and it will conduct electricity very perfectly. But if it's something, a electrolyte is there which is not forming ions, it is a weak electrolyte which does not dissociate properly, then it will be a weak electrolyte and it will be a poor conductor of electricity, okay. Next, size of the ions produced and their solvation. Size of the ions. If ions are too big in size, they will move slowly, okay, they will conduct slowly. If sizes are small, like H plus ions are there, which are small size ions, they will conduct fast, okay. Next, so nature of the solvent and its viscosity. So now you can imagine I have a tub like this, okay, here this is the solvent and you added electrolyte here, A plus and B minus, okay. Now if this electrolyte, if this solvent is highly viscous, means very thick solvent is there, then this A plus cannot move properly, right? It will have a lot of friction, it will have a lot of difficulty in moving the electrons, in moving through the solution. So if it cannot move properly, it cannot conduct electricity, right? Electricity is conducted due to the movement of ions. So if the movement of ions is facilitated or if it is smooth, then conduction will be good, right? Next factors what I have, concentration of the electrolyte. If there is too much concentration, if the concentration is very high, then what will happen? Then there will be a lot of collisions, right? A lot of resistance will be there. So there will be less conduction if the concentration is high. Next what I have, temperature. It increases with the increase of temperature. So if you increase the temperature, what will happen? These ions can move faster, right? They will have the increase in their kinetic energy, they can move faster and the conductivity will increase. So what we have understood, nature of the electrolyte. If I just want to write nature of the electrolyte, so what I'll write here, strong electrolyte will conduct better. Next, size of the ions, I can write small size will be better. If the viscosity, so if less viscous will be better. Next I have concentration, here I can write less concentration will be better. And temperature, as I've already said, if you increase the temperature, the conductivity will increase, okay. Now we will move to next topic, that is measurement of conductivity of ionic solutions, okay. So for measuring conductivity, we have seen the formula. What is the formula of conductivity? If you see, kappa is equal to 1 by rho into L by A, sorry, 1 by R into L by A, right? Conductivity is equal to 1 by R into L by A. So what all things I know? I need to know this L by A value and I need to know this R value. So if you have studied physics, to find the resistance of any conductor, we can use Wheatstone bridge, right? And we can find the resistance of that. But what happens in case of ionic solutions? There are two major problems. So first of all, in Wheatstone bridge, to find R, okay, I am talking about now how can we find the R of any ionic solution. Suppose you have been given with one ionic solution, okay, you want to calculate its kappa value, okay, and resistance you need to know, L by A value you need to know. So for resistance, what you can do, you can use Wheatstone bridge actually. But in Wheatstone bridge, what is there? First of all, you give direct current in Wheatstone bridge, and the second thing is that if there is a solid substance, if there is a metal electrode, you can connect it and calculate the resistance. It should be balanced. But if it is an ion, so there are two major problems that happens to calculate the resistance of this ionic solution. The first problem is passing direct current will change the composition of this solution. Okay, we should not change the composition. If we change the composition, the ions concentration will also change and the calculation will go wrong. So the first thing, if we pass direct current, the composition will change. Next, secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. This is liquid, right? So you cannot connect it directly with the Wheatstone bridge. So what is the problem solution here? So instead of direct current, we can use alternating current or AC. That solves the first problem. And the second one is, you can keep this solution in a container called as conductivity cell. Okay, so the second problem is solved by using a specially designed vessel called as conductivity cell. In the conductivity cell, you pour your electrolyte and then conductivity cell is connected in the Wheatstone bridge, and then you can calculate its resistance. Okay, so you can see here we have certain conductivity cell. So what exactly is conductivity cell? See, basically conductivity cell consists of two platinum electrodes coated with platinum black. Okay, so it has two platinum electrodes, and these have the area of cross section equal to A and is separated by distance L. Okay, so therefore the solution confined between these electrodes is a column of length L and area of cross section A. Resistance can be calculated using R is equal to rho into L by A. Okay, so you have this one. Okay, so you have this conductivity cell where you have platinum electrodes, okay, and the solution that is present between this area, okay, that is having an cross section area of L and an area, sorry, cross sectional area of A and length of L. And we have another also. There are different types of conductivity cell. These are some examples. Okay, so this conductivity cell can be used to calculate the resistance. Okay, now, but we have calculated the resistance now using what? So how can we calculate the resistance? Resistance we can calculate using conductivity cell. Okay, we'll use conductivity cell and connect it to the Wheatstone bridge, and we will pass alternating current. Now what about the cell constant? How do we measure the cell constant? That is again we need, right? So for measurement of cell constant also we have to do something. So first of all, this L by A term, that L by A term is called as cell constant, and it is denoted by letter G. Okay, just a minute. Yeah, and it is denoted by letter G, G star. G is what actually? G is, this is denoted by letter G star. It depends on the distance between the electrodes and their cross sectional area. Now we have the cell constant is usually determined by measuring the resistance of the cell containing a KCl solution whose conductivity is already known. Now what we will do is, we'll take this conductivity cell and you will pour KCl solution in that. Okay, and this KCl solution that you have taken, why KCl? Because its conductivity is known in all the different temperatures. So the conductivity cell is there, its cell constant is a constant value because it's just the distance and the length value, right? So you can take a conductivity cell, pour KCl solution whose, what is known? Whose conductivity is already known. Okay, so what I will do, see, you have a Wheatstone bridge like this. Please understand this one. You have a Wheatstone bridge like this, I'm just drawing a rough diagram. So here I'm taking my conductivity cell. Okay, so now what happens is, in this conductivity cell, okay, you can, when you put it in the in the Wheatstone bridge, you can calculate its resistance. Okay, now KCl is such a solution whose conductivity is known at different temperatures. Okay, so that means its kappa value is also known. Okay, so now if I know the kappa value, I know the R value. So I have this formula, kappa is equal to 1 by R into L by A. So I have kappa value, I calculated R value using Wheatstone bridge, then I can calculate the cell constant of this particular conductivity cell. Once this cell constant is calculated, now you can use different solutions and put down here, and you have the kappa value, sorry, you have the R value, cell constant value is already calculated, then we can calculate the conductivity. So I will like to summarize here. So conductivity, please understand this one properly. Conductivity has to be calculated using 1 by R into L by A. Okay, so first thing is to find out R. So R can be found out using Wheatstone bridge. Right, there are two problems here. First one, we have direct current, second one, it is a liquid. So what is the solution to that? The solution to this is, we can use AC current and we will use conductivity cell. Conductivity cell, a special type of container with platinum electrodes that we will use. We will fix that in the Wheatstone bridge, and then we will calculate the R value. Okay, now let's talk about this L by A, how to calculate this L by A. So for L by A, what is this called as? This is denoted as G star and it is called as cell constant. How to calculate this one? So what I will do, I'll take a particular conductivity cell and I will pour inside this what? Inside this I'll pour KCl, whose conductivity, whose kappa value is known at a certain temperature. Then what I will do, for that particular conductivity cell, I will connect it in the Wheatstone bridge and I will calculate its R value. Okay, so now for this particular conductivity cell, I have the R value, I have the kappa value, and I know that kappa is equal to 1 by R into L by A. So from this I can calculate the cell constant value. Okay, now suppose instead of, you have another electrolyte, for example CaCl2, you want to calculate its conductivity. So what you will do, again you will take in this container, what you will take, you will take CaCl2 electrolyte, you will pour. Cell constant, since it is a constant, it will remain same. You will put down again it in the Wheatstone bridge, you will calculate the resistance. So you got 1 by R value, L by A value is already calculated. Just calculate this and you will get the conductivity of that particular electrolyte. Okay, so that is how we can do the calculation. So now talking about on what factor does this conductivity depends. So conductivity depends on the charge and size of the ions. Okay, then it depends on the concentration of the ions, ease with which the ions can move under a potential gradient. Okay, so when you have two positive charge and negative charge, how easily these ions can move. Okay, so these are the factors on which kappa depends, or conductivity depends, or specific conductance depends. Fine. Next we will move to another term, that is molar conductivity. Now molar conductivity is the conductivity of all the ions present in 1 mole of an electrolyte. Okay, and it is formula is lambda m is equal to kappa by concentration, and here the kappa unit should be in S meter inverse and the concentration is in mole meter cube. If the concentration of, if the unit of kappa is in S centimeter inverse, then the formula changes here and it becomes kappa into 1000 by C. Okay, and the units of molar conductivity is S meter square mole inverse or S centimeter square mole inverse. Okay, so this you should remember. Whenever a question is given, kappa value you have to check it is in which unit. If S centimeter inverse, then kappa into 1000 by C. If S meter inverse, then kappa into kappa divided by C directly. Okay, fine. Next you can convert them internally. So you have 1 s meter square mole inverse, that will be equal to 10 to the power 4 s centimeter square, and if you have 1 s centimeter square, that will be equal to 10 to the power minus 4 s meter square, because you know 1 meter equal to 100 centimeter. So if I just explain this one, I have s meter square mole inverse, for example 5 s meter square mole inverse. Now how much is it in centimeter? You know 1 meter is equal to 100 centimeter. So I will write, you can write here 5 s, 1 meter is 100 centimeter, okay, square mole inverse, right? So I have here 5, then I have into, this is 10 to the power of 4 s centimeter square mole inverse. Okay, so that is how you can transform. Similar, if this is given, if you want to convert this one, divided by 10 to the power of minus 4. Okay, fine. Next we will understand, this is the next important term, that is variation of conductivity and molar conductivity with concentration. When I talk about conductivity, it is kappa value, and molar conductivity is lambda m value. Okay, so first the conductivity. Okay, so for this you should know what is actually conductivity definition. So conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between two platinum electrodes with unit area of cross section and a distance of unit length. So that means what? Suppose we have, see, you have a one second, yeah, suppose you have a container like this, and you have electrodes here. Okay, suppose this distance is 1 centimeter, okay, and the cross sectional area of this one is 1 centimeter square. In this much amount of volume of solution can remain. For example, the height of this one may be, suppose it is 5 centimeter. Okay, that means, so this is the total volume of electrolyte that is present in this area. Okay, now out of this, if I only talk about 1 unit, that means only this much. Okay, this is 1 unit of volume. Okay, in this total, what is the conductivity of, what is the conductance of this much electrolyte is equal to the conductivity, as I have explained in the rod. Same thing, but in terms of here we have taken in terms of electrolyte. So now what happens, let's understand this one in a easier way. Suppose you have this container, okay, and this is the electrolyte present here. Okay, not like this, suppose this is the electrolyte present. Okay, now in this, what we have is total number of ions I have is 5, or more ions are present. Now when you dilute it, okay, when you add more water to this, this is the this much area is 1 centimeter square and length is 1 centimeter, so it is 1 centimeter cube or unit volume. Okay, so this area is unit volume. Okay, so whatever is the conductance of this particular area, that is equal to the conductivity. Now how many ions are present? 1, 2, 3, 4, 5, 6, 7, 8. Now what happens? You diluted it. Okay, so I added more amount of water to this one. So now what will happen? Ions will move faster, they will spread throughout the solution. So what will happen now? Let me just erase this ions now. What will be the scenario? Earlier there were 8, okay. So now after diluting it, what will happen? Some will be present here, 1, 2, 3, 4, 5, 6, 7 and 8. Now number of ions per unit volume, has decreased, right? So when you dilute it, number of ions per unit volume that carry the current in a solution decreases. So if the number of ions per unit volume is decreasing, then conductivity will also decrease. Okay, so conductivity is basically the conductance of ions present in 1 unit volume. When you dilute it or when you decrease the concentration, the number of ions per unit volume decreases. So if the number of ions will decrease, conductivity will also decrease. Now let's talk about molar conductivity. So molar conductivity, what's the formula? Kappa by C. So when I add more water or when you dilute it, what's the formula of concentration? Number of moles by volume, right? So when you dilute it, okay, when you dilute it, what will happen? When you add more water, volume will decrease. If volume will decrease, I can say concentration will decrease. If concentration will decrease, molar conductivity will increase. Okay, so kappa, the conductivity decreases, but molar conductivity increases on dilution, both for weak and strong electrolytes. Okay, similarly kappa decreases on dilution, both for weak and strong electrolytes. Now we will see here something special about variation of molar conductivity for weak and strong electrolytes. Now what happens to the ions when we dilute it? So if you remember, for weak electrolyte, what happens when you dilute it? The dissociation increases. More number of ions are produced. Okay, for example, if you have, just let me take one example. If I have a weak electrolyte, okay, suppose here there were 10 moles, and when you have water of around, for example, 1 liter solution, in that you have added 10 moles of CH3COOH, then there were, okay, so only 2 moles have dissociated and we had 8 moles undissociated. Okay, 2 moles out of 10, total there was 10. 2 moles dissociated, 8 moles remain undissociated. Now when I made this volume to 5 liter, what will happen after that? 2 moles are undissociated and 8 moles are dissociated. Right? So you can see now number of ions that is dissociating is increasing on dilution, and why this is happening? That comes from your Lee-Chatterley principle. Okay, so when the number of ions has increased here, molar conductivity will increase. So that happens in case of weak electrolytes. So molar conductivity increases drastically. What about the strong electrolytes? Let's see. Let me take an example of NaCl. If I have 10 molecules, from the starting only it dissociates completely. That is why they are called at strong electrolytes. Right, they will dissociate completely. But then when you add, or this is in 1 liter, okay, but what is the condition? See, this is like this, Na plus is present here, Cl minus is present here. Okay, they are strongly attracted towards each other, or their movement is little bit restricted. Why? Because they are oppositely charged ions, they are attracting each other, they cannot move freely. Now what I will do, if I add 5 liters of water in that, so this water will flow inside. Then what will happen? I will have Na plus here and Cl minus somewhere here. So what is happening? You can see that now this inside this, or in between this, what is there? Water. So now this Na plus can move separately, Cl minus can move separately. Earlier what was happening? They both have to move in same direction, or they both have to move slowly and together. Now both are independent, they can move according to their own speed and can conduct electricity better. So that is why in strong electrolytes also the mobility of the ions increases. That is why molar conductivity increases. But in case of weak electrolytes, when you dilute it, the number of ions increases, and that is why molar conductivity increases. Okay, so this is important. You should know for why there is increase in weak electrolytes. That is due to the drastically increases due to the dissociation of ions increases, and here in weak electrolytes because the mobility of the ions increases. So you can see a graph here which shows the molar conductivity and the concentration. So concentration when it is decreasing, okay, this side the concentration is decreasing. You see for CH3COOH at 0, when the concentration was 0.4, the conductivity was somewhere here. But when it reached towards, or when you start decreasing the concentration, the conductivity increased to 400, okay, somewhere around 1 to 400. You can see what is the increase. This is the increase, right? Now, but if you compare for this one, this is for weak electrolyte. If you compare for strong electrolyte KCl, when the concentration was here, the molar conductivity was almost here. Now when you dilute it, the concentration, the molar conductivity increases to here for this concentration. So you see, when you decrease the concentration, the molar conductivity increased, but to a very small extent. Here it extended or decreased to a very higher extent, right? So that is the case that you should remember. Now we will talk about something limiting molar conductivity. Now as we said, when you dilute it or when you decrease the concentration, the molar conductivity increases, right? But when you dilute to the maximum amount, then the conductivity reaches a maximum value. That is called as limiting molar conductivity, okay? So when concentration approaches 0, okay, and the molar conductivity is known as limiting molar conductivity, and it is denoted by this symbol, okay, one naught is used. So this is the maximum molar conductivity that you can have, limiting value. After that we cannot have higher value, okay. Okay, now the graph that I have shown you, okay, this is drawn according to one equation, and that equation is called as d by Huckel equation, and it is lambda m is equal to lambda naught m minus a root over of c, lambda m minus lambda naught m a root over of c. Now here what happens, this value of a, so if you can see that for so let me just show you here. So you can see for this strong electrolyte, the equation is lambda m lambda naught m minus a root over of c, okay. So this is your y, this is your m, x and c, right? So what is x here? Root over of c is x, a is the slope of this line, that is the slope is a value, and lambda naught m is where it is touching the y axis. This value is called as your lambda naught m or limiting molar conductivity, okay. And we have y on the y lambda naught m on the y axis. So this is the equation through which we have drawn this graph for strong electrolytes. We cannot use this equation for weak electrolytes because you can see this is not a straight line equation, a straight line graph. Now there are certain things that you should know about this a value, okay. So this a value for a given solvent, it depends on different factors, okay, basically on the charges of the cation and the anion, okay. So for example, if I have NaCl, okay, Na is +1, Cl is -1, so it is a 1,1 type electrolyte. If I talk about CaCl2, it is a +1, +2 and Cl is -1, so it is a 2,1 type electrolyte, okay. Next I have MgSO4, Mg is +2, SO4 is -2, so it is a 2,2 type electrolyte. So like this, so all the type of all the same type of electrolytes will have same A value. Like for example, I can say that just a minute, yeah, I can say that NaCl is a 1,1 type, KCl 1,1 type, okay. Then you have, I have LiCl 1,1 type. So these all electrolytes will have same A value, okay. If I talk about, for example, MgCl2, this is 2,1 type, BaCl2, this is also 2,1 type, CaCl2, this is also 2,1 type. So these all will have same A value. Getting? Okay, now next we have Kohlrausch's law. Okay, so Kohlrausch's law tells you about, Kohlrausch's law is very simple law which says that the conductivity or the conductance of an electrolyte is due to the combination of conductance of its cations and anions, right? For example, if I have NaCl or if I want to calculate the molar conductivity of NaCl, it is due to the molar conductivity of Na plus and Cl minus. For example, if I have for CaCl2, so I can write molar conductivity of CaCl2 will be equal to molar conductivity of Ca2 plus 2 times molar conductivity of Cl minus, right? Cl is having 2 times of molar conductivity Cl minus, okay. Next, where this lambda m is used, it is used to calculate the alpha or degree of dissociation, okay, degree of dissociation alpha, which is equal to lambda m by lambda naught m, okay, and where lambda m is what? Molar conductivity, okay, and lambda naught m is limiting molar conductivity, and limiting molar conductivity can be calculated using Kohlrausch's law, this law, okay. So you have this Ka formula, C alpha square by 1 minus alpha, you can substitute here and we'll get this. And it is also used to calculate the lambda naught m for weak electrolytes. So you know that we have seen the graph of molar conductivity for weak electrolytes like this, right? It never touches the y-axis. So we cannot calculate it directly. So we have to use this lambda naught m value to calculate for weak electrolytes. I will show you that in the questions. So with this, we are done with the today's class. We'll do some questions now, and I want all of you to quickly revise all these formulas. Okay, I have given you all the formulas. Have a quick revision of that. Okay, take a screenshot otherwise, and let's do some brainstorming session with the first question. The cell constant is generally found by measuring the conductivity of aqueous solution of. So I told you which solution we use. We use very special solution KCET because its value is known for many of the things. So that is why we use this one to calculate the cell constant. Next, yes, the specific conductance. Specific conductance means kappa, right? I'll write the kappa value, which is 0.1. Sorry, the specific conductance of 0.1 m NaCl. So concentration is 0.1 m, and what is the value of specific conductance? 1.06 into 10 to the power of minus 2. Its molar conductance in ohm inverse centimeter square mole inverse. So you can see that the unit is in S centimeter inverse. So when the conductivity is in S centimeter inverse, what is the formula for molar conductivity? Kappa into 1000 by C. So let me just substitute here. So this I can put 1.06 into 10 to the power of minus 2 into 10 to the power of 3 whole divided by 10 to the power of minus 1, right? So if you see this becomes 10.6 and then 106. It becomes 106, or I can write it as 1.06 into 10 to the power of 2. Okay. Next, pure water does not conduct electricity because it is almost unionized. Okay, it does not have ions present, so that is why it does not conduct electricity. Next, the specific conductance of a 0.1 N solution is given. So specific conductance kappa value is 0.s centimeter inverse. Okay, and concentration is also given, but the resistance of the cell containing the solution at the same temperature was found to be 55 ohm. Okay, cell constant is how much? So we have just calculated this one, right? Kappa equal to 1 by R into L by A, or cell constant means this one. So L by A will be equal to kappa into R, or I can write down as 0.012 into 55, right? So if I solve this, I'll get 12 5s are 60 somewhere. So I'll get 0.66. You can just do the calculation. Okay. Next, I have the equivalent conductivity of 0.1 m weak acid is 100 times less than its infinite dilution. So equivalent conductivity. So molar conductivity and equivalent conductivity are two different terms. Molar conductivity we consider molarity. In equivalent conductivity you will consider normality. Okay. So it is saying that the equivalent conductivity is 1000 times less than that of infinite dilution. So at infinite dilution we have this one. Lambda naught is at infinite dilution, and then what is lambda naught? So let that be equal to lambda naught equivalent. Okay. So means we have this formula, dissociation is equal to what? Lambda naught m by, sorry, we have lambda m by lambda naught m. Now here they are saying that this value is 1000 times less than this value. So can I put like this by 1000, okay, this is this value, and then again I have divided by lambda naught m, right? This one and this one I can cancel, so I will have 0.01, which is option number C here. Next, the increase in the value of molar conductivity of acetic acid. Acetic acid is a weak acid, right, with dilution is due to. So when you dilute it, the molar conductivity increases. So I told you in weak acid it is due to increase in the degree of ionization, okay, more number of ions are formed, so that is the reason here. Next, the increase in the molar conductivity of HCl. HCl is a strong electrolyte, right, with dilution is due to. So strong electrolyte, what is the reason? The reason is the decrease in the interionic forces. Because they get separated, there is decrease in interionic forces and there is increase in mobility, okay. So that is why option number D here. Next, the molar conductivity is maximum for which concentration? We have molar conductivity formula, right? So if concentration is less, molar conductivity will be more. So which is the least concentration? B. So 0.001 will have the maximum molar conductivity. Next, we have the resistance of 0.01 m KCl solution at 298 Kelvin is 1500 ohm. So I will just write down this value. Resistance value is 1500 ohm. If the conductivity of 0.01 m KCl solution is this much, conductivity is into S centimeter inverse, okay. The cell constant is how much? I have to find this cell constant. So just now we have solved this question, similar question. Kappa is equal to 1 by R into L by A, right? So cell L by A will be equal to kappa into R, okay, and kappa value given to me is 0.1466 to 10 to the power of minus 3, and resistance we have is 1500, okay. So let's just quickly solve that. So I have here, I can just multiply first all the things. So 15 6 are 90, I have 9, 15 6 are 90 plus 9, 99, then again I have 15 4 are 60 plus 9, 69, then I have 15 1s are 15 plus 6 is 21, okay. Then I have 4 decimal places, 1 2 3 4, okay, and this I will get here minus 3 plus 2 minus 1, so I will get 0.219, which is option number A here, okay. Next, we'll see question number 10, the pair of electrolytes that have the same value of A. So I have already discussed how to find this one. So you can see NH4 is plus 1, Cl is minus 1, Na is plus 1, Br is minus 1. So these both are of 1 type, so they will have the same value. Here if you see, this is plus 1, this is minus 1, this is plus 2, this is minus 2. They are not same, so they will not have here plus 1, here minus 1, here plus 2, here minus 1, they are also not equal. Here plus 2 minus 2, here plus 1 minus 2, they are also not equal, okay. Minus 2, okay. So option number A here, okay. Next, lambda naught m for NaCl, HCl and NaAC are given. Calculate the lambda naught m for HAC. This is where you have to use Kohlrausch's law. So if you have remember, one of the application of Kohlrausch's law was to find the weak electrolytes lambda naught m value. So I want for HAC. So first let me write down all the values that is given to me. Lambda naught of NaCl is equal to lambda naught of Na plus and lambda naught of Cl minus, which is equal to 126.4, okay. Then I have lambda naught of HCl, okay, which is equal to 425.9, okay. Next I have NaAC, Na plus AC minus, which is equal to 91. Now I want to find for HAC, okay, that is equal to H plus and AC minus, right. So I want this H plus value, where it is, this one, right, 425.9, okay. Now see, when I I take this H plus from here. With that this Cl, so let me first explain without number. So see, from where I will get H plus? I will get from lambda naught of HCl, but when I take this one, I will get both of these ions. So I will take H plus and I have got Cl minus. Next, I need this Ac minus that is present here. So I will add this one, that is lambda naught of Na plus and lambda naught of Ac minus. Now you see that I have got H plus and Ac minus, but extra what is there? Cl minus and Na plus. So that I have to subtract, and where I can get that? That I can get from here. So minus lambda naught of Na plus and lambda naught of Cl minus. Now you can see this equation, plus Cl minus Cl plus Na minus Na, and I am left with H plus and Ac minus. So what all operation I have to do? I have to take this one, first is 425.9. Next I have this one, that is 91. Okay, this two I have to add, then I have to subtract, this is 126.4. You can just calculate it, 425 plus 9, 425.9 plus I have 91, so that is 5 plus 1, 6, 9, 10, 11, 516.9, and then I will subtract 126.4. Okay, so I have almost 390.5, which is option number D here. Okay, fine. So now after this I have given you some daily practice questions. So I think there are 5 questions. So try solving these 5 questions and keep commenting. These are all your PYQs question. So just put down in the comment section, and I will be discussing the answers of all these questions in my next class. Okay, so that's all in this video, students. Thank you for watching and all the best. Start studying, start preparing hard, because KCET level is going high, competition is increasing, and with our Sankalp batch you will be able to get the top rank. So thank you once again, and do not forget to subscribe the channel. All the best.